lecture by Bychkov, and Borja will continue exploring topological recursion and applications to Hurwitz numbers and other stuff. So please.
Yeah, thanks, Lena. So continue. So at first, your yesterday's questions about this H0, 0D, 0N, 0D. So I think so. So of course you can calculate obtain the spectral curve from this data from these numbers. But how to prove the topological recursion relations, I don't know. So
again, so of course you cannot prove, but we all know, having some experience with this stuff, that as soon as we know that topological recursion exists in the system, then the only thing we need is just the spectral curve.
Yeah, in this state. So if I think like this, yes. So we know how to compute the equations of spectral curve from this data. Yeah. You're right. Yeah. Okay. So what we had yesterday. We have from yesterday. We have this topological recursion procedure. So we have sigma is a complex curve. We have function. So we have a coordinate on this sigma coordinate on sigma, and we have two functions x and y, and we have a dx over x meromorphic form. So functions. Oops, sorry. Functions on sigma and like meromorphic one form with simple zeros. With simple zeros, and this p capitals is this zeros of dx over x, and the zeros of dy are away from P1, etc. Pn, and we have omega 0, 1. Omega 0, 1. Maybe I can write a little bit smaller. Maybe is y dx over x, and we have so of z in here in the coordinate, and omega 0, 2, which is dz1 dz2 over z1 minus z2 squared. And I could write so okay, let me write it this way, and the golomorphic involution near this ramification points of x, zeros of dx, sigma I of z is a holomorphic involution near pi's, and yes, and in this setup we have this. I suppose it was, yeah, it's written here. Yes, this formula, this recursion. So and in the case of simple Hurwitz numbers, we have in the case of simple Hurwitz numbers, we have simple Hurwitz numbers. We have sigma is just CP1 and X is Z e to the power minus Z and Y is Z. Okay, so and now I'm going to like reformulate this recursion and to maybe explain the meaning of this formula and explain like a way how you could really compute it. But maybe before I want to say a few words about for what benefits from this recursion you could extract, and then some maybe answers. So and examples. So examples of calculation for in the case of Hurwitz numbers. Let me start with examples. So again, in the case of simple Hurwitz numbers, the formulas looks like follows. So, for example, if you compute some omega gns for some small g, and then you obtain something like follows. So omega 0.3 of say it's d01 d02 over so, and for example, omega 1 of z0 is I hope I'm right. But so what is the important here? You see in these examples that these two forms have what is going on. I don't know how to. Sorry. Yeah. Okay. So in these two examples, you see that these two forms have poles only in this critical point P1, in the point z is equal to 1, which is 0 of dx over x. And it's some rational meromorphic function, meromorphic forms on CP1. So it's works, and it's a symmetric. The one it's a symmetric forms in this z variables, and so you really can compute. And then so again, if you now change variables to x variables again, so z of x, and take a Taylor coefficient in front of the monomial Taylor, and expand it in the origin in the point x is equal to 0 as a coefficient, you will have simple Hurwitz numbers. So when some benefits of some I don't know corollaries of benefits.
Well, if I can add something, just mention also that there is no singularity at infinity, no more.
Yeah. Yes. And important that we have rational expressions and only poles in the points pi's, which is in this situation like z is equal to 1. So at first I would say that it's a universal procedure, so very universal procedure. So these, like these and the same relations work in really very many different cases. As I will show in a very different cases of connected to the Gurwitz numbers, and as I mentioned yesterday, in the case of computing the volumes of moduli space with boundaries, and computing Gromov-Witten invariance, and matrix models business also in parallel of all these problems, and there are some generalization like and some Mazurowicz volumes of moduli spaces of quadratic differentials, and so on and so forth, and it's very nice and unpredictable that all this stuff are works in this setup. Also, in many ways, in many cases, it's really very efficient way to compute this invariance with this correlation functions or Taylor coefficients of this correlation function. Correlation functions, I mean this H, this let's say generating series for Gurwitz numbers in the example. So it's in many cases, maybe in most of the cases, it's very efficient way to compute HGN, or its Taylor coefficient. And third, that there are, of course, a connection with intersection theory on moduli spaces of curves. So if we connection, so like one would say that it's like a geometry representation of geometry, some corollaries of topological recursion connection to the intersection theory on MGN bar. So if you have a topological recursion for some problem, then this Taylor coefficients, this HGN, there is a procedure which allows you to obtain some concrete way to how to construct the classes which you have to integrate to obtain this Taylor coefficient. And in the case of simple Hurwitz numbers, it's famous DLSV formula. For the case of Hurwitz numbers, it is DLSV formula. Maybe I will not write it down here because of it's a different story, but very interesting. And this so this algorithm which allows you to connect, it's Giventhal and the works of Giventhal and Dunin-Barkovsky, Rontan, Shadrin, Spitz. It's a very nice and business and interesting. And the and there are, of course, a connection to the integrable hierarchies here. Connection. The integrable. So maybe I'll stop enumerating here, but I believe it's more and more you could add here. So for okay, so it's benefits and it's a, I would say, ongoing business, and very many people involved in this from different parts of maths to this story. Okay, so it's about the some corollaries and benefits, and now about the reformulation of the this recursive formula. Reformulation.
Could you please? I'm sorry to interrupt you. Could you please repeat once more how we get to the Hurwitz numbers from those formulas? The question is because Hurwitz numbers are actually Taylor coefficients of your spectral curve functionally inversed. It's a Lambert function. But how are omegas involved in this business? I don't understand.
So you obtain this omega gn, this this, and then you should yes, you have this z of x inverse series, and you have to expand it in the origin. So it's nice here that when we are talking about recursion relation, yes, today and then yesterday, we're talking about the functions near these points pi, so near z is equal to 1, yes. And then you should expand it in x variables after this inverse change of variables in x variables in the origin, which is different point, and this expansion will give you the Hurwitz numbers.
Expansion
so the Hurwitz numbers is a coefficient in front of x1 to the power and etc.
Yeah, but the coefficient in which series of z of x or omega of 3 or what? Omega of
3, yeah. So you
exactly should... This is a special case of 3,
yeah,
right?
because of I should maybe I should add here that this we had this HGN, yes, it's like some whirl mu HG mu, something like this, yes. And this omega GN is like some HG mu mu1, etc. mu n x1 to the power mu n minus 1 dx1, etc. dxn. Is it? Yeah. So this in x variables. x1. I'm sorry. I hope you could see something.
Yes, it's fine. We can.
So, and here we have these omegas in z coordinate. So you should re-expand in x coordinate, and you obtain these guys, exactly these guys.
Also, probably.
And then if you want erase these d's and divide by mu1, etc. mu n, and no, so
So maybe I also mentioned that it's connected Hurwitz numbers, right, Borja?
It's yes, it's connected Hurwitz numbers. Yeah. So, Yura, am I answer your question?
Yeah, thank you. I understand that.
Okay.
So, and why do we need all of the omegas if because without them we can't compute O3 or what?
Why we need these omegas? What?
Other omegas than omega 3, or they have some independent interest.
So, I mean, omega 3 gives us only like
no, sorry.
Yeah.
We need all of them.
Yeah.
Thank you.
Yeah. Okay. Great. So, reformulation. Let me maybe just maybe theorem that the existence of topological recursion is equivalent to the following. The existence of the topological recursion equivalent to the following. So that we have this omega GNs, which are global rational one form in each of its arguments and symmetric in this arguments. And this, so that we have this forms global meromorphic one forms in each omega GN in each of its arguments. So in each of, so it's a form on Cartesian, or I would say tensor product of sigma to the power n, but in fact we do not change this dz1 and dz2 etc. But as a rational function, as a rational function, is asymmetric in these variables, and symmetric in so possible poles of omega Gn only in P1, etc. Pn, these zeros of dx over x, and it's like a intro, and the two so not intro, this second this conditions usually calls projection property. Projection property. And in fact, this formulation of the projection property is like only if sigma is a CP1, if sigma is a surface of high genus, then this projection property formulates a little bit harder. But in the case of CP1, sigma is CP1, it formulated as I did, and in my lecture, sigma will be CP1, so I want to write it in this way. The third is that principal parts of the poles of omega gn is odd with respect to the involution. So the principal parts of the poles in P1 of omega gn of omega gn so it's symmetric, so in each variable you can say in first variable in first variable the principal parts are odd. So with respect to the involution sigma, so it calls it's a linear loop equation, and you could write it like follows. So omega gn of z1 z2 n plus omega sigma of z1 z2 is holomorphic. So near sigma I near pi, yes. And the last condition that it calls the quadratic loop equation, and it's about the also that some form is odd, and this form looks very similar to the expression in the recursion relations, and it's not a coincidence. So the expression omega g minus 1 n plus 2, we have z0 z0 zn plus some so it's more or less what was in the recursion relations, but with so z1 times omega g2 plus 1 z0 z2. So also this expression is an odd form in the first variable, also with respect to the involution sigma. Is the odd form in the first variable. With respect to sigma. So sigma I near pi, or you could write here, add here this involution and write it as follows. So you could let me write it this way. You could add here sigmas and here sigma, and say that this expression is holomorphic in the first in the variable z0 in the first variable, and so what is it calls it's a quadratic loop equation, and if okay, maybe I can copy this. Up. Ten. Yes. Oops. Okay. And erase a little bit. So let me erase the first part of the recursion, this residue. But this, what is written here in the brackets, yes, it's more or less the same as written here in quadratic loop equation. The difference is in this prime here. So yesterday this summation was overall such decomposition, except of if g is equal to 0 or I1 or I2 are empty. And here I allow all guys, and it's the difference. And we see in 5 minutes that it's important, and it's why it's more or less equivalent, these formulations. So okay, these two, this theorem, maybe I may for a moment zoom out a little. So what we had here, what conditions? So we have this, if we have some problem, some enumerative problem, and when we compose this generating series and obtain this omega gens, and if we know omega 01 and omega 02, so we know a spectral curve, and the knowing a spectral curve is like some miracle, because of we don't know how to, there are no algorithm which gives you spectral curve equations if you have numbers. But if you know it and you obtain this omega gens, then you could prove this statement. So you could prove that this omega gens, if you know that omega gens are good in some way, so you could say something about the structure of this omega gens. So you should prove that they are rational functions, and the poles only in these points, P1, etc., Pn. And then that's linear loop equation, which says that this combination is holomorphic, and the quadratic loop equation, which says that this expression is holomorphic, or in a little bit different language, that this omega GNs are odd form with respect to involution, and this this expression without sigma also an odd form with respect to the involution. So in fact, the later means that. So in fact, how it is. So how we usually prove this, you could take some. You could describe a space of functions with such conditions and prove that these omega GNs lie in this space of functions. So what's how to reformulate topological recursion, and why this is true? So why these conditions are equivalent to the topological recursion? It's not too hard to understand. And so let's start with the quadratic loop equation and rewrite it a bit. So maybe I could leave it here and take this guy. And okay, so how to obtain TR relations from linear loop equation and quadratic loop equation and projection property. So if we have this expression, which is an odd form, let me write in more details this sum. So let us extract from this sum our omega GNs, which we are looking for. So how we obtain omega GNs, omega GN plus 1 in my notations. If G1 is equal to 0 and G2 is G, or vice versa, and also here if I1 it's from 1 to n and I2 is empty. So this exactly those summands which are missing in the recursion relations, and then we obtain something like follows. So omega G minus 1 and plus 2 the 0 the n plus some prime of these guys plus 2 times omega G n plus 1 times omega 0 1, because of we obtain here. So we have here I plus 1 I2 modulo, so I2 plus 1 and modulo I1 plus 1. So we obtain here 1 if one of those guys is empty. Okay, and then let me instead of this yes, instead of this omega 0,1 of z0 and here z0 zn, and here these guys, and let me write instead of this omega 0,1, it's the odd part of this omega 0,1. So instead of omega 0,1, it's let's write the odd part of it. So omega 0,1 of z minus omega 0,1 of sigma of z. So you may think about simple Hurwitz numbers and only one ramification point of x, only one 0 of the x over x. And so what we did if we change this guy to this guy, we add some in the whole expression. We add some even and regular stuff times omega gn plus 1. So it doesn't change the condition of linear loop equation. So this omega gn plus 1 times some regular, even regular stuff again has odd principal part in the first variable. So the condition of linear loop equation holds. And we can, and now we can rewrite again this quadratic loop equation in the following way. I want to move this to the different side. So what is the different other side? Other side means that it is some odd form, and we obtain something like this. So we obtain that omega g n plus 1 of z0 zn is equal to 1 over these guys. So I change minus, move minus here, times what we left here. So times these guys. So yes, times these guys. Plus some prime of this product of two omegas E1, E2 is equal to E. Plus what is the if I write here the equation, is plus some even and regular summands with respect to the involution in the first coordinate. So what we finally obtain here, we know a lot about omega gns. So omega gn, in my notation omega gn plus 1, uniquely determined, so the odd part of omega gn plus 1 determined uniquely by this quadratic loop equation. So the odd part of omega gn plus 1 determined uniquely because of, so we will just write it down, yes, by induction. This is the odd part of omega gn plus 1. By quadratic loop equation. But from the linear loop equation, we know that omega gn plus 1 odd form with respect to this involution. So there are no even part. Therefore, we obtain so odd part of principal part of the pool of the pool of pi with respect to sigma I in the first variable. And by the linear loop equation, we know that omega gn plus 1 has only odd part. So we're done. We know finally from quadratic loop. So from the projection property, we know that this omega gn has poles only in these p capital points, pi capital. So in z equals to 1 for the case of simple Hurwitz numbers. And quadratic and linear loop equations say that we know the principal parts of these forms in each variable in each of these points. So we could, up to a constant, we could reconstruct this. We know this omega gns, and the constant, we fix the constant like staging that they are zeros in the origin, for example, and they're done. So this is how it works. And here you see this. So this equation, it's more or less a topological recursion relations. So, and this residue which was there means that we erase this even and regular part. So, and here, so that's all. We get an algorithm to compute these omega gns, and of course, except of instead of using those recursive relations, it's more convenient to think in such a way. So to think about this ordered regular and even parts of these forms, and maybe about this space of functions which I mentioned. Okay, so I would say that I more or less prove this not prove because, but more or less prove this theorem about reformulation of topological recursion relation. So okay, I think it's the time to ask maybe some questions, because now I want to switch to the Fock space formalism and to generalize a little my my Hurwitz numbers. So by now, what we have, I hope we know that if we have some enumerating problem, we and if we know the spectral curve equation, that we know how to, so by some first initial data of our numbers, we know how to compute all of them by this recursion. And also know how to really work, how to really its recursion works because of this reformulation in terms of quadratic and linear loop equation and projection property. So I have like at least 5 more minutes. And so if there are no questions yet, then let me continue to. So now I'm going to generalize a bit the setup of simple Hurwitz numbers and introduce the Fock space formalism, which is also very useful to. In fact, my goal for this part, it's I think it's should be part 2 in my plan, which was at the beginning. In a general setup, so I have like a very general, I will say Hurwitz numbers, but it's some generalized Hurwitz numbers. My goal now, if I have some generalized Hurwitz numbers, and I know the spectral curve equation, equations of the spectral curve, equations. Then I want to obtain some, I would say, nice or nice formulas for WGN to to prove the topological recursion, to prove the topological recursion in a very general setup. And for this goal, it's very useful. It turns out that it's very useful to use this Fock space formalism. So yes, maybe I can set up this general setup and then we'll stop. Maybe the link for this part is our paper, explicit closed algebraic formulas, and something, etc. by Bychkov, Donin, Barkovsky, Maxim, Kazaryan, and Shadrin. And yes, so we and as I said, we know the equations of spectral curve, and now we have x of z is equal to z times e to the power minus psi of y of z, and the y of z is in general any formal series. And psi here also, psi of y is any formal series. And sigma is CP1, as I said. So simple, for example, you see that simple Hurwitz numbers are obtained if you take psi, so y is equal to z. So all s k, if k greater than 1 are equal to 0, and s1 is equal to 1. So y of z is equal to z, and psi of y is equal to y. It's simple Hurwitz numbers. And for maybe I can write some more specializations of this psi and y. So if psi is y to the power r, is r spin. So very all known cases of Hurwitz type problems fit into this general setup of this spectral curve. Log 1/1 minus y, it's monotone Hurwitz numbers. Log 1 plus y, it's a strictly monotone Hurwitz numbers. Buscemi-Lucifer numbers also obtained in such a way. Oops. It's a log 1 plus y the power m, and maps and hypermaps also. Maps and hypermaps. And the specializations of y gives so that if z it's just simple numbers, if it's z to the power q is orbifold, and in the case of any polynomial k from 1 to d, it's a doubles usually calls double weighted Hurwitz numbers. So all known cases of Hurwitz numbers fit into this setup. So okay, and let me. So now where I want to write the generating series. Yes.
Yes, just please, like 3 minutes, no more.
Okay. So maybe I can stop here just to start.
Maybe
with,
it's a good good place to stop actually. because Borja is still have one more lecture tomorrow.
Yeah, it's only one, but I hope I will manage to explain something more. Yeah.
Okay, but first we definitely want to thanks Borja. And please questions.
I have a stupid question probably. So you talk about a reformulation of TR relations, right? But this is not the reformulation of Kontsievich and Sollberman.
No.
Which what I understand is more than just much more than just a reformulation. So this is also a question for Leonid. So do you know? So do you have a suggestion about where to read something? I mean, the best introduction, let's say, to the setup done by Kontsievich and Sollberman of the topological relations. If you have suggestions.
I don't know. I know. I remember that so I once found some recording of lectures of Bertrand in R about this. About maybe you can find it, and maybe there are some links.
Okay.
This is my answer.
Well, maybe I can say that we had the text just after Kontsievich and Sollberman with Jürgen Andersen and Gaëtan Barrault, Nicolas Rantan, so where we try to explain it in more details with some examples and so on. So it's an archive, same year 2017.
Okay, so it's the paper that starts with ends with ABCD, right?
It's ABCD,
okay.
Yes.
Yeah. Okay. So thank you so much. Thank you. Yeah.
But actually, yes, Alessandro, and I actually have a related question to probably Alessandro, but a little bit different, Borja, because we are still in CP1, right? In all these exams, so we basically think about all these generating functions or differentials as having just one branching point.
No, so it may be many branch points, and there may be not non-simple, but we live in CP1.
No, stop. Then I but your Bergman kernel is
it's just the same. The same. DZ1, DZ2 were Z1 minus Z2 squared minus dx1 if you want dx2 over x1 minus x2 squared. So all works perfectly well with many branch points, with non-simple branch points. Yes, but in CP1, yes.
Okay, if you have more than one, of course, that's different. But for simple Hurwitz numbers, there's just one branch point, right?
Yeah, and simple ramification, yeah. And
simple ramification, yeah. And this makes it equivalent in Giventhal formalism to just Kontsievich.
To GLSV, yeah.
So
to Kontsievich-Witten, you obtain like the Kontsievich-Witten, the spectral curve like follows like x of z square over 2 and y of z.
Yes, and we can actually obtain the spectral curve just by basically constant shifts of times, which makes the corresponding generating function automatically a tau function of KDV hierarchy.
You mean from what? From what? Starting from what?
No. It's slightly more older stuff. So we have also times of KDV in this case. And basically the claim is that we obtain, but we can literally obtain this spectral curve out of the spectral curve for Hurwitz numbers, or vice versa. It works in both directions.
Yes.
Some holomorphic transformation. So we read out shifts of times from this holomorphic transformation of coordinates, local.
Yeah. In what you're saying about it works perfectly well in this setup also, because here we have KP tau functions of, say, hypergeometric type. So yes, it's straightforward tau function of KP.
Okay.
In this general setup also.
Okay, nice. More questions from someone? If no more questions, then let's thanks Bori again. I think it's quite illuminating. This series of talks is quite illuminating.